Our second speaker in this morning session is Professor Tian Lan from the Chinese University of Hong Kong. He will talk about the symmetry enriched topological orders. Let's welcome.
Thanks for the introduction and for the addition to the Congress. I'll discuss a recent work. Actually, I should describe it's not really some new work, but the reorganization of what we have done in the past 10 years, maybe. And this was done together with two of my students, Yue and Wang Ye. And also, please feel free to interrupt me if you have any question or if you feel any concept that is not clear. I expect the talk will be hard to follow. Okay, this is outline, and let me begin with the motivation of this work. Why we propose such a notion of kind of category of SE orders. So the study of any symmetry of some mathematical or physical object. Let me just use some abstract symbol V here. It is common practice to consider some group, right? Some group and a group homomorphism from this group to the invertible endomorphism of that object V. This is common practice, and this is also called a representation of the group on V, right? And if we care about quantum mechanics, and we take V as some vector space or Hilbert space, then you would like to take this endomorphism to be just linear maps. Then take the invertible linear maps or the general linear group. In that case, if you collect all the representations, you have this group representation category, which is just the functor, linear functor from the looping of G, Bg, to the category vector space. Okay, and I would like to call this this idea to study symmetry as the representation principle. But unfortunately, in the study of block spaces, we want to study the symmetry of block spaces, or it has a name, this symmetry enriched block order. We find or we encounter some problem. If we directly apply this so-called representation principle, and for example, I'll come back to this case later, and here I'm just giving a brief discussion. So if you take so mathematically, if you take a module to the category C and consider a symmetry, then it's a natural guess to consider the some group acting on C by braided order equivalence, right? So this is a higher group homomorphism because you want to promote G to a monodal category. Then you consider monodal functor from G to the also equivalence functors on C, and which is also a monodal category. But if you study just mathematics of this thing, it's always fine. But if you interpret it, see as a category that describes a 2+1D equivalent order, and you want this thing to describe the as 2+1D SEP, then you find something wrong, which here is just so-called gauge or hoop anomaly. So you can associate a in this case a four cycle, I think, to such an action. So this feature tells us that if you consider the representation of G in the two category of modular to the categories, such a representation category, this object fails to be a good description of 2+1D SEP. I'll come up with discuss more details of this later. It's also fine, but okay. The point of this talk is to convince you what is the appropriate target category to pick. Okay, so that's the kind of motivational idea of this work, and we would like to revive this representation principle, this simple principle that applies to any symmetry. But for this physical application of SCT orders, you have to take some good category. You should, in the previous slides, is all the module tensor categories, they form two categories, and if you take morphism to be the Morita-equivalence, that is not a good candidate if you want to study SCT orders. And a short answer here, if you want to study 2 plus 1 SCT orders, what you should take? You should take a so-called invertible separable 3 category, which is the 5 stooping of some module tensor category. And all the SCT orders. Yeah. Oh, so what I'm trying to classify is the collection of all the operators. So in one particular order, you have surface operator, you have line operator, you have all of them, and I collect all of them and consider what symmetry can act on those operators. Then this thing is one SET, one symmetry in reversible order. So, yeah, so you actually assign symmetry to all those. You have a way to assign your symmetry to some of the operators, and each consistent assignment is the SET. And I'm classifying all of those. Okay, so this kind of higher level thing. Okay. And BG is considered as a 3 category. Yeah, BG is 3 category. But it's kind of a trivial, both the higher morphism are trivial. Only the one morphism is G, and the object is also trivial. Okay, so this kind of another motivation that we want to achieve kind of a similar story as what happens, for example, in classical mechanics, that you can derive from a simple Newton's law, and of course, at the cost of some complete mathematics, calculus, and you can combine them to derive everything in classical mechanics. And here we want to do a similar thing, that we begin with this formulation. That's, you should, of course, specify the groups that bend the symmetry and specify which underlying order you are interested in. And then you can derive everything about the interplay between the subordinate phase and the symmetry. And in more detail, those means, for example, the symmetry breaking, what are the symmetry chart, the symmetry invariant operators, and how do you stack different SETs, and how do you gauge. In particular, that means volume extension, and also the information which you may hear recently, how you extract the so-called symmetry, topological field theory, or symmetry total order. So everything is encoded as a substructure or sub-information in this category of SET orders. So that's the kind of some elegance we want to achieve. Okay, and here is the take-home message. We will be kind of for simplicity in this talk, we'll focus on the finite Bosonian symmetry G, and you'll see later that generalization is straightforward. So let me assume outside. If it's space-time, I believe it still works, but I think there's more we can do. Okay. So the dimension is space-time dimension is n plus 1, and you figure symmetry G. And then what are the so-called category of SCT orders? Is given by this functor category. It's actually a representation category of group on some higher category. And in particular, if you want this underlying browser to be anomaly free, then we require this X to be an invertible object with respect to the tensor product of higher vector space, which means if you take X tensor with its skew, you get the tensor unit. Okay, what is the underlying integral order for an object in this function category is maybe a little bit different from people usually understand. You should take the suppose you take a functor, and then if we want to extract what is the word operators, or a modular or a non-degenerated n-1 category, you would like to take the base object, which is BG here, and then take this image and then loop twice in this X. So those are all the codimension 2 or higher operators in your third order. X is actually a collection of all the third orders of the same weight class. Depends on both G and X. Yeah. Depends on both two things. Yeah, we actually are puzzled of how to call this X thing. Is can some further anomaly in addition to symmetry? Yeah, yeah. Yeah, in your paper we said this GSEG with anomaly characterized by X. Yeah, you have two inputs to fix what the function. Yes, yes, yeah. So this equivalence is actually promote BG to some linear category, and the equivalence is due to the fact that the looping and completion are left adjoint. And after you do that, you can actually play, because this is this is just a separate category, higher category, and you play that by anything you like. So you can already describe a lot of other symmetries, but I'm just talking about this simple example, simple symmetry. Weak. Okay. So as I said, here it's like for Newton you have to know the mathematics calculus. Here we need to know the mathematics of higher. I call that higher linear algebra as mathematics about higher vector spaces. But as audience asked just now, I have to apologize that this math is not fully developed by now. So in a sense, if you, for example, if you ask me what is the full explicit detail of, say, 5 WAC, then as far as I know, there's nobody who have written down all the details. So basically, we can only do calculation in a physical way for 4 WAC or lower. But nonetheless, I would tell you some operational way to deal with those higher vector space. I don't care about the explicit details inside those categories. I'll just tell you how you can play with them, how you can do algebra of them. And the definition, due to Galto, John Frey, and Kong Zhenhao, of n+1 WAC, is just the n+1 category of separable n categories, or linear curvy complete in categories which are dualizable. So that's some generalization fancy generalization of finite dimensional vector space. Okay, and the thing we care about for all the operations that we use in this work, I think just two things. One is tensor product. The other is taking linear functors that maybe I just call linear maps. So like finite dimensional vector space, which means n equal to 0, one vec. For those higher vector space, you can take tensor product. Suppose x and y are two n+1 vector space. You can take tensor product of them, and this is still an n+1 vector space. And you have a unit, which is just the n vec at n-1 level. Okay, at n level, lower than this n+1. So n vec is the tensor unit. If you multiply or take the tensor product of n vec with any vector space, you get x. This is similar as if n is 0, then this n vec means net number. Okay, and another property is the linear functors from n vec to from the tensor unit from x from n vec to x. This is just the shorthand notation for this morphism in n+1 vec. So all the linear functors. This thing is canonically equivalent to x itself. So if you are not familiar with this, you can think about what happens in vector space if you consider the linear map from the class number to any vector space that's canonically isomorphic to the vector space itself. Okay, and also all those vector space, higher vector space has two. And in the vector space case, the do is just given by the linear map from B to C. So here it's the same. All the linear functors from X to the tensor unit n vec gives you the do category. And in the higher category case, we have a further equivalence due to the embedding. So this do is just the opposite category of X. And if you take unit embedding, you have an equivalence because you are not consider the general unit lemma. You are taking the target category as some finite realizable category. Okay, so those are all some familiar operations we know in vector space. And the fourth one is that the linear functors is just a matrix. So the linear functors from x to y is just the dual of x tensor y. So you can think about this as if they are vector space, then you have like a n-dimensional vector space, m-dimensional vector space, then the linear maps are n by m matrix, right? It's like n-dimensional vector space, tensor m-dimensional vector space. And here it is similar. It's just the y tensor x off. But this tensor is actually this higher tensor product has become complicated. You have a lot of contingent descendant from this construction. Now to go to those details. Okay, so those are the things that just the generalization of Euro vector space. There are something more, which are the so-called looping and looping. Because here we have a number n that tells you which level of category it is, and also there are also some number integer for the monoidal structure. So looping is defined. So if you take the category X and pick object inside X, and the looping is defined to be so loop X is defined to be taken the endomorphism in the category of the object. So this is looping, and clearly, if you do looping, then suppose X is n category, then this form category is n-1. It is n-1 category, and moreover, you introduce a mathematical structure, a algebraic structure, a monoidal structure on this n-1 category. So this is looping. If you begin with a category, you get a monoidal n category, then you get a monoidal n-1 category. And in particular here, because we assume X is in some nice linear category, after looping, you get a multi-fusion n-1 category. And if you loop twice, if you have a fusion category here and take its tensor unit, and you loop that, you get a braided fusion n-1 category. So, sorry, n here, n-1 here. So this is the one operation that more than the Euro-vector space. And we have also have a kind of weak inverse to that, so-called delooping. So how to do that is you take a category which is at least monoidal, greater monoidal, or symmetric monoidal, at least monoidal. Then first take this BC, which is one-point delooping. It has a single object with endomorphism as just its original category, and then do a Harvey completion. So this is actually an important mathematical step to ensure that this category contains all the physical observables we want to study. And this will do this deloop after this Harvey completion by sigma c. And this looping is left inverse to delooping. That's clear. And also, delooping is a left adjoint. It is not left inverse. It's just a left adjoint to the looping. Okay, and this basically, maybe there are also a relatively sublime, but I don't have time to explain. These are all the operations we are going to play with the higher vector space. You don't really need to know the details inside those categories. Okay, then I think I have to discuss a little bit about what's the physical meaning of this abstract category. And I put this blue words is not necessarily the unique. And in fact, in this talk, I will give you two interpretations. Okay, so as a first kind of maybe geometric picture, you can think the objects and hieromorphisms are just labels of logical defects of varied dimension. So this n+1 is just the dimension. And the level of object morphism are just the codimension of the defect we label. So if you do that inductively, then an object or a zero morphism in n+1 vec is just the n+1 dimension defect. Not really a defect, it's actually occupies the entire space-time. So you can also think that as n+1 dimension phase. Now, one morphism is a codimension 1 defect. It's ND defect between you specify x, y. That's this category is the category defects between x and y. And also you can do that again and again. The two morphism, if you fix two ND defect, of course you have to have consistent domain and codomain. I'll omit that detail. The two morphism is then also a defect, n-1 defect between f and g. You can do that again and again until the n+1 morphism, which is zero-dimensional defect in space-time, which is actually a operator. But because we do everything in a logical way, it's actually a equivalent class of local operator, not maybe not exactly a physical operator. Okay. Then the special tensor unit is corresponds to the trivial phase or the vacuum, and the tensor product is the stacking of defects. And we have the stacked defects. You can consider their defects as the you can do that component wisely. And the most important thing I want to elaborate on is this property. This is a generalization of C to B equals to B, right? So all the functors from n vec to x is a category is equivalent to X. So you can see we have fixed interpretation to this one. This means the defects between vacuum and X. So you can call that, for short, that's the boundary conditions of X. And as a category, it is equivalent to X itself. So what does this mean? That means if you consider the object morphism inside X, you have such equivalence, you can interpret those object morphisms as the boundary condition and the higher defects on the boundary conditions of X. So this formula itself is some kind of boundary block correspondence. Okay. Any question? So an object in X, based on this equivalence, you can interpret that as a boundary condition of X. And the higher morphism are just higher fundamental defects. So this may be confusing because I may be shifting from the point of view that X is an abstract label of n+1D space, or as a category of boundary conditions of that label. I maybe shift my point of view. So I want to clarify this more here. Okay. Then we can check the boundary block correspondence. So what are the operators for the defects in the bulk X? By our previous interpretation, you should compute the morphism from X to X, right? So this means that you are taking morphism in n+2 back, and these categories are just all the full dimension 1 defects in X, of course, including the higher ones. So this is the defects for the operators in X. And in general, this is not trivial. Only when X is invertible, this is trivial. And the boundary conditions is the functors from n back to X. And this is naturally a left module over the category of operators in the bulk. And if you check the universal property of center, which I didn't explain, the center of this boundary category is just the operators in the bulk. So this setup of parametric space itself already encodes the boundary block correspondence. Right, that's already here. So I explained that. So X, suppose that our total dimension is n+1. Then one way you think X as an abstract label of an n+1 dimensional space, and also in that. Okay, and then this category are the category of n-dimensional defects or n-dimensional boundaries of X. But because of this property of vector space, you know this category is equivalent to X. So the objects morphism in X are also the boundary conditions of that n+1D abstract label. So I know there is confusion when I do this work with my students. We kind of constantly become confusing about what we're talking about. So this X, it encodes the information of both the bulk and boundary. Okay. It's just a module. It's one side in this convention is left module. Okay, and yeah, to further explain this, I want to call you to rethink about the case n equals to maybe 0, so a 1 vec. So this, what it is, this is just the unilinear algebra. It is where we play with quantum mechanics. And I think maybe most of the students, when they first learn quantum mechanics, will ask what are the quantum states. And we actually don't have any physical description about what is quantum state. Besides that, maybe X state corresponds to some observable. So here, if you're thinking in this logical correspondence way, you'll find what is so you consider this case that operators from C to V is the same as the vector space itself. But you can think C to V, those operators as the boundaries in space-time from nothing to some non-trivial quantum system. And they correspond to the state in this quantum system. Okay? So then you have such an interpretation that quantum states are the boundary conditions in space-time of this 0 plus 1D quantum system. So it's already there. So these things are even already there in quantum mechanics. Okay? In other words, you don't know what are the quantum states. You just give its boundary some name, and superpose them. You get this quantum system. Okay. Then I'll come to this part that this holography when you consider symmetry. So in the previous slides, we discussed this perspective categorical defects, right? And in that picture, you should think this category as a defect between these two categories, between these two n+1D phases, the boundary conditions between these two things. And if you further compute the defects for operators inside these two objects, you'll find, maybe let me begin with X first. Because we assume X is invertible, then the defects inside X is trivial. But the defects inside this sigma n back G, after some calculation, you find that it's actually the n+1D G gauge series, of course, discrete G gauge series. So this is nothing but the so-called symmetry TFT or symmetry order, if you heard those names from other perspective. So so this means, okay, of course, I'll try to convince you later that this category is exactly the category of XEP orders. So then the same mathematical description, the same mathematical object has two interpretations. One is the boundaries of this GK series or this symmetry TFT. The other is just category of SE orders. So this is, I think I provide a point of view that why this idea of symmetry TFT works is just have same mathematical description as this representation category. But you have to somehow go to this higher category picture to really see that. And we have furthermore a mathematical version of a categorical version of the relation between center and Morita class. So, this results in the case of future 1 or 2 category have been done by mathematicians by Eno and Thibault Decobit. And I think also in the work, recent work of Kong Liang, maybe he'll talk about this tomorrow. We gave such a reformulation. If you consider fusion n categories, T and H and D have the same trivial center or E1 center, then this is equivalent to that T and H are Morita equivalent up to some invertible object. So that means T modules and H modules, which are also sigma D, sigma D looping of T and sigma H. They are equivalent, but you need to stack a reversible object in n+1, n+2 back, then they are equivalent. So these two are equivalent. So in other words, recall our structure that if you take linear maps, linear operator, linear functors between these two, you just take the matrix, right? So this has a similar form of this thing. You have sigma n back G, just U, and the stack with some invertible thing. So this structure exhausts all the boundaries of this one, which has the same center as sigma n back G. So this is the center of this part. So you can think this as the n back G as T, and then sigma T stack some all the possible invertible several categories. You exhaust all the fusion in categories that have the same center with T. Okay. So this theorem kind of backups the equivalence here. To consider all the boundaries of SymTFT. Of course, you have to be allowed to change this X. You have studied all the symmetry irreducible orders. Okay, so these are roughly all the maths I need to introduce as background. Next, let me go to the examples and try to convince you by examples that this works by listing at least all I know about SETs. So let's first consider the cases in low dimensions. If you have n equal to 0, 0 plus 1D. So this is the formula. And you want to substitute n equal to 0. And that's 2 vec, right? You want to take an invertible object in 2 vec. You have only one choice, which is vec itself. So the 2 vec, explicitly 2 vec is two category of finite semi-simple linear categories. And in that case, the tensor product is just the linear tensor product, and only vec is invertible in that category. And then if you just use that formula, you go back to this representation category of some group. Okay, so that's the the description of quantum system with symmetry when you don't consider the complexity of dimensionality. So that's the 1D, then 2D, then equals 1. Then now you want to take you consider the things in 3 vec, and what is the invertible object in 3 vec? Again, there's only 1. So this result, if I translate that physically, this result means there's no third order in 1 plus 1D system. Okay, there's only one invertible object, which is 2 vec. Okay, then you consider this category FCT. The direct translate into the true replication of the screw. And mathematically, we already know the result, the clustering result. The objects in 2rep-G are parameterized by 2 data, by a pair. One is a subgroup, the other is 2 cocycle on this subgroup. And those mathematical results also agrees with physical classification of 1 plus 1 dimensional phases with symmetry, which is you have 2 physical data. One is the unbroken symmetry, so you are allowed to simultaneously break G from G to a subgroup H. Then this unbroken subgroup can cause the symmetry protected phase, whose invariant is omega, this 2 cocycle. Okay, so in those cases, we don't have ambiguity of taking some not true irregularity here, but in beginning in 2 plus 1, we have to do that. So I'll explain in more detail about the story in 2 plus 1D. So 2 plus 1 per order, we know that they can be characterized by model-tensor category. And as I said, the naive way to consider symmetry on this method object is to consider the action by braided auto-equivalence. It seems natural, and also it really works. It's part of the story because, for example, the symmetry factorization is already encoded in this description, although I will not expand on that part. But still, this description is incomplete because you can have the Hooke's anomaly. And by again by they have already proved you can promote such a representation to a monoidal 2 functor from 2 vec G with some twist of focus cycle. And always propose this rho to such a 2 functor. Then from this 2 category, fusion 2 category to sigma C, to the delooping of C, which is also a fusion 2 category. And this invariant is just the Hooke anomaly. If you want your symmetry to be gaugeable, then you have to require this this obstruction to vanish. Okay, and when that vanish, what you got? You got a monoidal 2 functor from 2 vec G without any twist, 2 vec G to sigma C. Okay, and then you just deloop that both sides again. You get a functor from sigma 2 vec G to sigma twice C, and this when C is model-tensor category, sigma twice C is invertible object in 4 vec. So that is, maybe this is really the initial motivation of this work. So a 2-dimensional third order without gauge anomaly corresponds to a functor in 4 vec from the symmetry to some invertible object. And the other direction is also clear. If you take invertible object and loop that twice, you get a model-tensor category. So a functor, from BG to this X. After you do this looping twice, you get the more traditional description of 2 plus 1 SE on. Okay, so then we have verified this proposal at least in low dimensions. Next, let me discuss all the let's basically follow the story of BPCW. We consider group action on model-tensor category and require that you can consider add symmetry defect and negate them. I'll show later the relation to model extensions in the gauging part. Okay, so then as a promise, I want to tell you how you extract all those various properties of symmetry from this category. And you can see they are actually very natural. If you get familiar with those maths, you can guess that by yourself. So first, the defects between SET. So how do you define defects between SETs? It's just the higher multiplies in this category. Very simple. Definition very simple. Although, as I apologize in the beginning, n is large, I don't know how to compute them. But conceptually, this is very simple. And in particular, if you take X to be n plus 1 vec, the trivial invertible category, then this functional category just becomes the module categories over n vec G. This may be too abstract. Then let me tell you a more explicit example, and you can, if you don't know the math, you can just look at the first sentence. If you consider the so-called surface order, 2 plus 1 order, with some anomalous G action, which means this G action can have some omega 4 non-trivial Fourier cycle, then I'll tell you this data is actually, in our formulation, it's a morphism in this category. Okay, and of course here you need to do some calculation. You want to first take the trivial GSPT order, which is characterized by the forgettable function from 3 back G to 3 back. And then what is the 3 plus 1D SPD order? You want to take a actually it's still a 3 back G to 3 back to the center of this category, but I will change the perspective to consider this emergent object as the module over 3 back G. This is the GSPT, and here is already confusing because people usually don't think SPT can have some. So this is actually information about the boundary of this SPT. Anyway, after you fix these two objects, these are 3 plus 1D GSPT, then the defects between them are just you take morphism between module functors between these two module category, and after a bunch of calculation, you find this is exactly this category. So, so that means this monodal functor gives you an object in this category. This is isomorphic to the defect between these two. Okay, actually physically people know this well, that the surface order is the boundary of the 3 plus 1D SPD phase. And now in this formulation, you can verify that directly. Just take 3 plus 1 SPD, one is trivial, that's non-trivial, and compute their defect, you find this category. And the important thing is, in this category, you have more choice other than just monodal functor from 2 back G to sigma 6. You can take, for example, some non-simple, degenerate boundary condition, or something that only with the equivalent to C. Okay, so that's one thing. Then the second thing I will talk about is I call that charge category. And by that I mean all the operators that are invariant under the action of the symmetry. And how to do that is, again, very simple. First, you should fix an SET, fix an object in this category, and then loop this category on F, which means you take the endomorphism from F to F. So that's, you can see this is actually a special case of the previous general defects. You just consider defects within a specific SET order. And this by definition is also the relative center of the monodal functor underlying this F. So if you loop F on the base object, so this is a monodal functor from syntax G to the corresponding looping of the image of F. So I'll use speed for the monodal category in this part also later. Okay, and then the charge category is just the relative center of this monodal functor. And you can think what this functor do is assign the G symmetry, assign the label of G to some operators in your order, in your following fix. And by relative center, it just means in a very rough way speaking, it's just operators in B that commutes with the image of this group. It's a very rough description. In higher category picture, you have to replace this equality by some higher structure. That's very complicated. But anyway, again, this idea is straightforward. So if you didn't follow, you can recall that how to define the operators when your symmetry is unitary. If you just consider all the operators that are invariant that are under the conjugation of the unitary symmetry. So here this F is invertible. S has invertible fusion rule. So this you go when this symmetry is invertible, you can conjugate this Fs on the other side. That means this relative center is just the operator that invariant out of the action of the symmetry. Okay, and the example, trivial example actually, if you consider the trivial phase in vec G baguette to in vec, then the relative center is just the higher representation of G. And I didn't show you other example, but if you can compute more exotic examples, you'll find by this charge category you can see whether the symmetry is spontaneous broken or not. Only when the charge category is in rep G, that is symmetry is not broken. You can find other assignment that gives you, for example, you can find the SET that the charge category is in vec G. In that case, that means your operators invariant in your system is a symmetry defects instead of symmetry charge. Okay, so this is a charge category. Okay, and next, the symmetry breaking. Actually, explicit symmetry breaking. So from the charge category, you can see spontaneous symmetry breaking. But what if you want to explicitly break the symmetry? You can just use a embedding map to have subgroup embed into your symmetry, then just pull back because mathematically this is just linear functions. So you just pull back all these linear functions here from G to X to H to X using some embedding. So this is just explicit symmetry breaking. And of course, more generally, you can consider any group and not necessarily embedding. You can change the symmetry by this pullback. And the stacking of SET is done by first just stack them without any interaction to the usual the inverse product, higher than inverse product. And you get SET order with double the symmetry, G cross G. And then if you break that using the diagonal map, you get the same symmetry. And if X, suppose X and Y are invertible, this X tensor Y is still invertible. This is how you naturally define the stacking of SET orders. But again, I have to apologize that it's hard to compute that for the time being. It's hard to exactly compute that. Okay, then the final topic is ungauging, and I'll discuss this in more detail. So we need some kind of more knowledge about what is this looping of the vec G. By the theory of condensation, the objects can be identified. Objects in sigma vec G can be identified as algebras in this fusion category. So then, what is gauging? You can think this in a different way. Gauging, you have vector F from F to F from n vec G, sigma vec G to X. Then there is a base point, right, coming from VG, this base point. And if you restrict F to that base point, you get a monodal functor from G to some fusion category. But you can also change your base point, because after you do this Karobi completion, this category has a lot of objects. And those objects correspond to algebras. And you just change your base point. You consider here, consider F, loop F on some non-trivial object, which is also an algebra. Then what you got? You got a monodal functor from the bimodule of A in vec G to the bimodule of FA in the target. So this is gauging, and maybe this is too simple and you don't believe me for the moment. But physically, I will try to say this: you have algebra, and gauging is condenting that algebra. And mathematically, you shift from F to another monoidal functor, which separable algebra or condensation monad. Right. Yeah. Yeah. Okay. And just a side remark. Because we consider fusion category symmetry, then you have a functor and you loop that functor on some other object, and then you loop again, you get back to the original functor, which means any gauged theory. Gauged theory just means this loop A on some other object. Any gauged theory contains the same information as original theory, which is you loop on the base the distinguished object. So that is why, actually, that's why the expression in terms of gauging, in terms of model extension, works for SED orders. Okay. Then let me, for one thing, I want to generalize what I discussed about, and also discuss the gauging in this more generalized context. So we have been considering the symmetry, a simple symmetry G, but now you can see we can consider a generalized symmetry, any fusion category T, instead of just the vector T. So any fusion category. And also, this target B can be any fusion category. We don't really require that B to be some anomaly free thing. The center of B can be non-trivial. And more generally, that's the really interesting part. After you upgrade to this perspective, important to think about. Can you even generalize away from this hierarchical space framework? If you want to consider like continuous symmetry or confused theory, what should you use for DNT? But anyway, let's be more restrictive, consider fusion categories or multi-fusion categories. And then the SET is just corresponds to monoidal functor from D to B, monoidal n functor, I functor. And that also corresponds to a linear n plus 1 functor if you loop both sides. Okay? And even in this case, all we have discussed previously still works, except that stacking will require you have some additional structure on the symmetry. Okay. Sorry. Okay. Then how do you do the general gauging? Basically, you have a monoidal functor from T to B, then you take relative center of that, and this gives you a sandwich. If you bend this part back, it gives you a sandwich. And this monoidal functor is equivalent to this sandwich, because you can think so this sandwich equivalent to B after you take center of everything, and you just trivially insert T into this sandwich that also gives the monoidal functor. So these two perspectives are equivalent. And how do you do gauging is you need to take a T module or take algebra in T and compute the center of everything with respect to those. So it's drawn here. So you have a symmetry, monoidal functor, B, and this together fix an SET order. And you do some algebra in T, and then take center of everything. So this ATA is actually also a relative center, take a center of everything. So what you got is another fusion in category, which you can see, you can call that the gauge symmetry, and another monoidal functor, and another underlying order. And this process is manifestly invertible because this is just a special case of Morita-equivalence. So this is how you prove that's invertible. You just take the invertible bimodule, and you can, from the gauge theory, go back to the original theory. Okay. So here are some examples. So this is the ordinary gauge theory. Of course, we have to recover that. Ordinary gauge theory, you just take the functor and you take this trivial module over index G, you get enriched as a gauge symmetry and also the gauge theory. And you can twist this thing by some n+1 cycle. So then this part is SPT. To gauge that, you get the twisted gauge theory, the degravitation gauge theory. So these are the two important cases. Then the 2+1 DSEP. As I explained, you should consider model functor, two functor from 2 vector to sigma m for some module of the category. Then if you do gauging for this case, this charge category is you first do G parameterization on M, so you got a so-called module tensor category over rep G, and then you loop that, you got the fusion two category. This is the charge category. And the gauge symmetry is 2 rep G. And if you then collapse this two, collapse the sandwich on this fraction, this gauge theory is exactly the looping of a module extension of this charge category. And of course, you can go back. If you already know module extension, know the gauging, then you can ungauge this one-form symmetry and recover the G action on the module tensor category. Okay. Okay, so there are other examples you can after this kind of trivial example. You can do partial gauging, you can gauge a subgroup, or even generally you can gauge any algebra which is not very large in your building category. And you can also do higher gauging, so you can gauge higher dimensional defect in a anomaly theory. So you don't need to require this to be trivial. That means P is some boundary of such defect in the non-trivial higher in the non-trivial box. And there's also a interesting thing we call lower gauging. This higher lower is kind of co-dimension. So lower gauging means you can also gauge the bulk. Gauge the bulk of this theory B you are interested in. And why we introduce this is because we find, at least in this framework, if you want to gauge from a parity, you have to consider lower gauging. So maybe we have before we have a more complete theory of higher category in the higher vector space framework, you have to consider gauging the bulk to recover, for example, the 16-fold way of gauging 2+1 fermion invertible phase. Okay, that's all. So this thanks for your attention.
Maybe we have several short questions.
Be generalized to fermionic cases.
For fermionic cases, you need to change both the symmetry and the target category. So the symmetry, my opinion is that the fermion parity is different symmetry than, for example, the global G symmetry. So in this case, it always appears in the lowest level. So you want your T to contain an operator or at the it's hard to count. So I should say you should always require S-back, superback space. Then you loop that to the same level as T is embedded in the symmetry. So
also different.
X should also contain that. So that's the modification you need to do for fermionic system. Then everything else are the same. You just the input, the symmetry, and what is kind of order without symmetry. Those notions are different. You have to accommodate the fermionic nature in that part.
So we have a concept called the category of quantum liquid, which we show that you can ignore the dynamical part, right? That category is equivalent to the topological data. We thought that this should be equivalent to the category of SET if you don't specify the particular generalized symmetry, if you allow them to vary, I mean the T. So my question is your category of SET the same as the category of quantum liquid that we are thinking about by allowing T to be general and varying?
I think short answer actually, I don't expect that.
Uh-huh.
I think the symmetry actually plays an important role. Maybe even for quantum liquids.
Or we could also, symmetry. Yeah, we could in the category of quantum liquid, we can also, well, fix the fusion patterns.
Ignore the symmetry, totally break that. But the interplay between symmetry and your quantum liquids is another story, and it has more information than merely quantum liquid. So this formulation allows you to change your symmetry arbitrarily. You just and recompose any function to change the symmetry. That's always allowed. With different symmetry, specific different symmetry, I think you have different description of what that symmetry happens in a.
I know, yeah. Perhaps let me reformulate the question. And maybe I could say to take the category of quantum liquid, but fix the fusion category symmetry.
That thing has problem in. I think in the paper we will mention this subtlety. You can consider a fixed t, but you change the x, then there's some problem. So, for example, if you consider two different say x and y, then what does it mean to consider? Maybe let me do the blackboard. So we can only define the defects for the same x. So that's the morphism in this category. But what if you just care about, say, take SET here, what's the defects between them? Then it's very subtle. We don't know how to define that. There's no natural way to connect kind of SET in this or X is kind of some lower dimensional anomaly part. It's hard to connect the SET here with SET here. So there is something need to be further studied. So even if you fix symmetry, I think there's still out of this.
Okay, if there is no more question, let's thank the speaker again.